Good afternoon. Today we'll be talking about temperature sensors. Temperature sensors are very important because temperature is influencing everything. Hold on, I have to think. Yeah, okay, now it's working. So, temperature will influence all other variables that we will measure, and therefore we will start with temperature sensors. And today we'll be talking about contact temperature sensors. So it means that the sensor itself is in direct mechanical contact with the object where you measure. And next week we will be talking about non-contact temperature sensors, so how to measure temperature at a distance. I will show you basically two types of contact temperature sensors. One will be thermocouples. They are producing voltage as a function of temperature. And the other group will be resistive temperature detectors, which will change electric resistance as a function of temperature. So let's start with thermocouples. We will have some experiments in the lab as well. One group already did have this lab last week. So thermocouples are very different from all the other sensors that you will see for temperature. And the major difference is that thermocouples measure temperature difference. So they do not give you directly the information about temperature, but they give you temperature difference between the two ends of the thermocouple. That is very important. The thermocouple is composed from two dissimilar metals typically, although it can be created also with non-metallic elements. But I will show you only metallic thermocouples. So here the thermocouple itself is created typically by welding of two dissimilar materials. And like this you create the hot junction. Hot junction is the point where you measure the temperature. So this will be in your application, this will be in the pipe or in the tank or whatever you want to measure temperature. The thermocouple wire is created with the same materials like the thermocouple connection itself. And there will be different materials, and we will have also different thermocouples. So the thermocouple material is very important. Typically, the thermocouple looks like this. So this is a thermocouple. Those are the two dissimilar metals, and they are welded at one end. And the other end is connected to a terminal box like this. And all this is then placed usually in a thermal well. So the thermocouple itself is protected from mechanical and chemical damage with the thermal well, and the terminal box is then here in this box, and from this place you connect it to your control system. As I said, thermocouples are typically produced by welding. So you initially take a thermocouple wire, which may look like this, for example. So this is a thermocouple wire, and you can weld it at one end. And normally it is done with a capacitive welding. So here I have a welder, and now we'll weld a thermocouple, as you will do on the lab class. So here there will be one electrode over here, and a second electrode is here. And this is basically a bank of capacitors that is charged to some voltage so that it can give me some charge. And now I have prepared the wire, and I will be welding the hot junction. So let's try it, and now let's see what will happen. Nothing will happen. Hold on, I probably. Yeah, it's probably not detecting the contact correctly. So let's try it again. Yeah, okay. So like this, you will weld your own thermocouple on the lab, and this is creating the hot junction. This is sitting in a thermal well. Then you typically have a terminal box, and you have some connecting wires between the terminal box that is at the thermal well side and between another terminal box that is at the side of the control system. So you can have two options how you can connect this. Either you use the thermocouple wire, which is the same material as the thermocouple wire you have here. This is typically done for, let's say, normal thermocouples that are not from special materials and that are not very expensive. So then you have directly the same thermocouple wire that is connecting those two places together. In some rare cases, you can use something that's called a thermocouple compensation cable. The difference is that this compensation cable is not from the same materials like the thermocouple. And this is used especially for very expensive materials like platinum, typically. And for those special thermocouples, the thermocouple wire itself would be very expensive. So here you use this compensation cable, which in a small range of temperatures has similar properties to the thermocouple wire, but definitely not in the whole range. Here are some examples of thermocouple wires. How do they look like? So you can see that they have some shielding, typically from metal or from plastic, and that you can choose different diameters. The diameter, of course, will have an effect on the properties. We will see it a little bit later. And then at the end, you have a second terminal box, and here is where you connect your control system. And the signal, the information that you read is temperature difference. So you are basically reading a voltage with a voltmeter or something similar. And this voltage is a function of temperature difference. So you need to know, you are looking for temperature T1, but you need to know temperature T2 as well. So this is very different from all the other sensors. If, for example, T1 would be the same as T2, you would read voltage 0. So this is called the cold junction or also the reference junction. And you can see that if the temperature of the reference junction will change, then we will get different voltage, and this will be very bad. So for this reason, we will also see how to work with this. Typically, it's put in some thermostat or you measure it with some other temperature sensor. Now, thermocouples, they differ in the material from which they are built. And there are two very common thermocouple types, thermocouple type K and type J. And you see what are the materials. So type J, one wire is from iron, and the other wire is from an alloy that is called constantan, which is an alloy of copper and nickel. This is the most common type of thermocouple. And the second very common type is called type K. And you see it's an alloy of nickel and chromium and nickel and aluminum. For all thermocouple types, the voltage that you get as the dependence on temperature difference is very small. You see here, this is the sensitivity roughly from 0 to 100 centigrades. And you see that thermocouple type J gives me like 52 microvolts per centigrade. And for thermocouple type K, it's a little bit smaller, let's say 41. So the voltage that you read is very small, and you typically need to amplify it right at the thermocouple, because this small voltage would be very difficult to be transferred for longer distances. So it will be very sensitive to electromagnetic interference as well. The sensitivity typically is given like this, so some voltage per centigrade or per Kelvin, and it's very small. The data that you see here those numbers are assuming that the thermocouple voltage is linear, which is not. So this will work in a small range of temperatures, but it's definitely not working for larger temperature ranges. You will see it in a minute on the charts. Thermocouples are letter coded, so type J, type K, type T, and so on. And they are also color coded. So by looking on the thermocouple wire itself, you can tell what thermocouple wire it is. The wire that I gave you here was thermocouple type J, which has black color. Unfortunately, there are differences based on the ANSI standard and IEC standards. The J-type thermocouple, it's the same, so it's black. That's good. But the second most common type K, one standard says it's yellow, one says it's green. So you will also need to look into what standard are you following, and this will give you the colors for the thermocouple wires. For example, here I have this pink thermocouple wire. This should be type N, according to this one. So it will have a little bit different properties, but it's still a thermocouple. In this table, you can also see that the individual wires are color-coded as well. The reason is that we need to watch for polarity. If the temperature at the cold junction is larger than the temperature at the hot junction, then you will get a negative voltage. So the polarity of the voltage will also give you the sign between T1 and T2. We will definitely see this in the lab experiments as well. So for this reason, you see here that we have the plus and minus wires marked, and the plus lead in this case is iron, and this is constantan. In the table, you can also see the ranges where you can approximately use the thermocouples. So the most common thermocouple type here, they say up to 1200 centigrades, although typically the thermocouples are used for small temperatures, let's say like 800, 1000 centigrade, something in this range. You can see that the thermocouple range depends on the material, and if you want to measure really high temperatures, such as 1768 centigrades, you need to use different thermocouples. And here, for example, it's type S, and you see it's a platinum, that's one wire, and the second wire is platinum and rhodium alloy. So this will be the case of a very expensive thermocouple, and the case where you should use the compensation cable. So then, in this case, the thermocouple will be only within the thermowell. Here you will have the high temperatures, and from the terminals over here you will use the thermocouple compensation cable. We can also see where those thermocouples can be used. So for example, type J, it says limited use in oxidizing atmosphere at high temperatures, and also not recommended for low temperatures. The reason is in the nonlinearity of the thermocouple, as we will see in a minute on the chart. For example, type K, here they say vacuum atmosphere or reducing atmosphere is limited use, but it can be used in oxidizing and inner atmosphere. And you can read all the others. So for every application, there will be probably a different type of thermocouple that will be suitable. This is an example of a thermocouple table, as you will see in the lab classes. So this is just for no reason at all thermocouple type K, and here you see we have the thermocouple voltages, and here are some temperatures. And note that here this voltage is always related to some reference, and this reference is typically 0 centigrades. So that's why here they say that the reference junction is at 0 centigrades. So for example, if I would measure a temperature in a tank with oil which has 100 centigrades, and my reference junction would be at 20 centigrades, then the difference is 80, and I would need to look for 80 centigrades in my table. I don't have 80. This is for negative temperatures. This is for positive. So let's say I will be looking for 250 centigrades for some reason. So here you see it's 10.153 millivolts, and this is the temperature difference. So 250 would be the temperature difference plus the temperature at the reference junction. If you don't know the temperature at the reference junction, you can just read the temperature difference, but you don't know what temperature that actually is. If you put those tables in a chart, you will see steady state characteristics, as we will do it on the lab. And here you see that different thermocouple types have different properties. Typically, the positive temperatures, that's more linear than the negative temperatures that you have here. The two most common types, type K and type J, are here, so black and green. And you can see also the ranges. So type J goes all the way up to roughly 1200 centigrades. And it's mostly linear, although it's not very, but it's exactly linear. In the negative temperature range, you can see here, okay, it's definitely non-linear. So that's the reason why you should not use thermocouple type J for negative temperatures. For thermocouple type K, you see it goes to a higher temperature, roughly 1350. And it's mostly linear here in this range, and the same non-linear part over there. So those are the examples of steady state characteristics as you will measure on the lab class. The properties of the thermocouple also depend on the wire diameter, and if you have a larger wire diameter, you will have a larger time constant. So a small thermocouple with a thin wire will react faster to temperature changes than a thermocouple made from a thick wire. So this is represented here in this chart. This is transient response, and here you have time. Here is the output signal, and like this you have the thermocouple diameter decreasing. So if you have a small diameter of the wire, you see here it's reacting quite quickly. If you have a large diameter, the time constant is definitely larger. On the other hand, there is also a dependence between a maximum temperature range, where you can use the thermocouple, and the wire diameter. And it's exactly the opposite, like this. So if you have a larger wire diameter, you can use it for higher temperatures. And if you have a very thin wire, it will be usable for lower temperatures as well. So if you select a thermocouple, you should take all this into consideration. What should be the range? What should I measure with it? In other words, how fast do I need to acquire the readings? As I said, thermocouples are protected in thermowells. So it can look like this. So a thermocouple with a thermowell. And there is also a difference that relates here to this end, how the thermocouple is installed in a thermowell. So we can have three options. One is that we take directly the thermocouple wire and we do not use a thermowell at all. That's the bare wire. This bare wire will definitely be very fast. So if you really if you want to read with high sampling frequency, then this is the best option. You do not have any thermowell, which will prevent the heat transfer, and your time constant will be very small. On the other hand, you don't have any protection for the thermocouple wire, so it can be used only in non-corrosive applications where you don't have any pressure. The second option is that you install the thermowell, and inside the thermowell you have the thermocouple, and the thermocouple is not in direct contact with the thermowell itself. So it's looking like this. You have some insulating material. Here, insulation material means electrical insulation, not thermal insulation, of course. In this case, you have a very good protection against corrosion, but the heat needs some time before it's transferred into the hot junction, and this will increase you a lot the time constant of the thermocouple. Something in between is the grounded junction. The grounded junction means that the thermocouple itself is in direct mechanical contact with the thermal well, and the thermal well in this case is typically from metal, so it has a quite good heat conductivity. So there is an electrical connection between the thermocouple wire and between the thermal well. This can decrease you the time constant, but it can bring you problems with electromagnetic compatibility, because here this is like a big antenna, and this will pick up electromagnetic interference from all around you. So it's typically need some testing if you choose this, which is more secure, or if you choose this if you need faster response. Those are some examples of thermocouple probes. I have here some thermocouple probes. So this is type J thermocouple probe, and probably this is a thermocouple type J as well. The length of the thermal well depends on the application. And last slide related to thermocouples is how do you handle the problem that it gives you the temperature difference. Either you place the cold junctions in a place where you maintain constant temperature. So a thermostat, for example, typically you place it in an ice bath. An ice bath, as you know from physics, maintains a constant temperature until all the ice has melted. So here you have an ice bath, an ice water mixture, and this has a constant temperature. The advantage of this is that the voltage that you measure is directly what you read in the tables. You don't need to subtract anything, since the reference junction is exactly at 0 centigrades. The disadvantage, obviously, is that you need to maintain the ice bath. So when the ice melts, then it's not having the constant temperature anymore. So a second option is that you heat this bath, typically with oil, and you heat it to a constant temperature that you maintain with a thermostat. So you heat it for, let's say, 50 centigrades, something above the room temperature, so that you don't have any influence from temperature changes. If you don't do that, if you connect directly the thermocouple wire to a meter, you have a second thermocouple here between the thermocouple wire and the copper terminals. And this will cause you trouble when this is changing temperature. So then when there will be changes around the voltmeter, you will read different voltage and you don't know if this is caused by the changes around the hot junction or by the changes around the meter. So this is the recommended solution. Here it does not happen, because although we have the two thermocouples here and here that we add, they both have the same temperature, and this will give us 0 voltage that we add to the thermocouple voltage here. So this is a way how you can eliminate the changes of temperature around the cold junction. A second option, or third option, would be that you have an additional temperature sensor that measures the temperature around those terminals. This is also used in some instruments, that they have a different kind of temperature sensor placed near the terminals. So then you have a temperature reading, and you add or subtract this to the voltage that you have from the thermocouple. Some questions? Okay, so now let's go to resistive temperature detectors, the second group. This is the most common sensor used for accurate industrial applications. The resistive temperature sensors are based on changes of electrical resistance with temperature. See, it's called RTDs, so resistive temperature detectors. And it's basically an electric resistor made from typically platinum that we measure the electrical resistance. In small temperature ranges, so typically within the range of plus minus 100 centigrades, we can consider that the electric resistance is a linear function of temperature. The coefficient of proportionality is called temperature coefficient of resistance, and is defined like this. So it's a resistance for 100 centigrades minus resistance for 0 centigrades. This works quite well in those small temperature ranges, but it's not working very accurately for higher temperature ranges. So for higher temperature ranges, you need more coefficients, A, B, C, D, or eventually even more. And this works for platinum sensors just with 3 coefficients in a quite large temperature range. For different metals, it's not as good as it could be, so we are using more coefficients than those 3. The most common metals used for RTDs are platinum, nickel, and copper. Platinum is the most common one because it's very accurate, but on the other hand, it's also very expensive. So for cost-sensitive applications, you will definitely not use platinum sensors, but you will use either nickel or copper. It will have some disadvantages, as we will see. Here you see the temperature coefficient of resistance. So platinum has roughly the same coefficient as copper, so it means that it's changing roughly the same resistance with temperature. Nickel has about double the temperature coefficient of resistance, so this means that it will give you higher sensitivity. In other words, the electrical resistance will change more with the changes of temperature. And the third column is resistivity. So it's the resistance of a wire with a certain length and diameter. And here you see that platinum and nickel, they have roughly the same resistivity. So this means that it will give you roughly the same resistance when you have the same diameter and same length of the wire. On the other hand, if you look on copper, it has much smaller resistivity. It's a much better conductor. So if you want to build a copper sensor with the same resistance like nickel and platinum, the wire needs to be about 10 times longer. So the copper sensors will typically have a much smaller initial resistance than the other sensors from nickel and copper. So let's start with platinum. Platinum is a very stable metal. It's not changing that much in time, so this will be very good for sensors. They will be stable in a long term. So if you repeat the measurement in 1 year, in 2 years, they should give you the same results. Platinum has also a relatively high electrical resistance. So this means that you can use a small current that is flowing through the sensor. This will be also very good. But the most, let's say the largest advantage of platinum sensors is that they are interchangeable without recalibration. Since platinum can be manufactured very accurately, in purity I mean, then you can interchange the sensors in your application. It means that you calibrate your application for a platinum sensor. If you need to change it for some reason, then you just take the same type with the same characteristic, you put it in your application, and that's it. You don't need to do any calibration. This will not be true for other especially for the copper ones or the semiconductor sensors, as we will discuss at the end today. Platinum sensors are noted in this format. So PT stands for platinum, and then there is a number. And the most common sensor type is called a PT100, and this number means what is the electrical resistance for this sensor for precisely 0 centigrades. So a PT100 has precisely 100 ohms for 0 centigrades. The second most common type of sensor is a PT1000, which obviously has 1000 ohms for 1000 centigrades. There are different types like a PT50 or PT5000, but the PT100 is really the most used one. The steady state characteristic for a PT100 is nonlinear for a larger temperature range. A PT100 can typically work from somewhere between minus 250 centigrades up to, let's say, 600 or 800 centigrades, dependent on the construction. So in this entire range, it's definitely nonlinear, and you need to use all those coefficients from the equations, so A, B, C, D. But if you look on the component, on the coefficient values, you see here that B is roughly 5 orders of magnitude smaller than A, and the same is for C. So if I am in a small temperature range, then this is a very small number, this is a very small number as well. So within a very small temperature range, let's say plus minus 100 centigrades, we can consider a PT100 as a linear sensor. If you are using a larger temperature range, then no. This is the steady state characteristic for a PT100. You see from roughly minus 200 centigrades to roughly 800 centigrades. As I said, it depends on the construction. In all cases, the sensitivity for a PT100 is 0.39 ohms per centigrade. It's a little bit different between the European standard and between the American standard. One has like 0.38, one has 0.39. The accuracy of a PT100 is the largest for all temperature sensors. So the international temperature scale is defined for some fixed points by using the PT100 sensor. There are two accuracy classes, Class A and Class B, and the two accuracy classes differ in price. Class A is more accurate and more expensive, and Class B is less accurate and less expensive. The difference is achieved by different purities of platinum, but typically you see 99.999% platinum is used. In this table, you see what you can expect from a PT100 sensor. So let's say Class A sensor, it has for 0 centigrades, it will definitely have 100 ohms, but it can measure with accuracy of plus minus 15 centigrades. The Class B has roughly twice is larger interval, so roughly 0.3. But even if you go to the maximum temperature, 600 centigrades, then you can measure this within 3.3 centigrades, plus minus. So this is about 0.5%. So 0.5% is okay for Class B. Here you see for Class A, it's roughly 0.2%. So a PT100 is the most accurate sensor in this temperature range that you can use. As I already said, there is a large difference between standards in Europe and in the US. It's not saying that something is less accurate or more accurate. It's just saying that you will get a different sensitivity for those temperature sensors, and this will limit the UD interchangeability. So you should use always the same standard and keep using it, because if you replace the PT100 that was made by some standard with a different one, it can cause you a large error in your reading. This is an example. For 0 centigrades, both standards, they have 100 ohms precisely. But then there is a difference for larger and smaller temperatures, and this difference is quite significant. Here you see for 600 centigrades, the difference between the American and European standard is about 4 ohms. So 4 ohms, when you look at the sensitivity, which is, let's say, 0.4, will give you an error that's larger than 10 centigrades. So just by using the wrong standard for your application, you may introduce an additional error that is about 10 times larger than the accuracy of your sensor. So if you use this table, 600 centigrades, okay, class A, I'm able to measure within 0.4 centigrades, but just by using the wrong standard, you can add additional 10 centigrades of error. So this is very important, because today you can buy sensors from all around the world, but if you need it for a specific application, then you need to take this into consideration. Okay. A very common type for a PT100 is made from glass. So a glass PT100 is a cylinder from glass. I need to find it first. I had it here somewhere. I don't see it currently. It's here. So it's a small cylinder from glass. Looks like this. And inside the cylinder, you have a very thin platinum wire. The typical diameter of the wire is like 0.05 millimeters. So it's a very thin wire. So that's here. It's wound in a special way that's called bifilar winding. And this kind of winding will limit you the inductivity of the sensor itself. So we are looking for changes of electrical resistance, and we don't want any additional inductivity in the sensor. Then you have some terminals also from platinum wire, and all this is typically placed in a thermowell that looks like this. So sensor is over here, and then you have a terminal box over here. The temperature range for the glass PT100 is roughly 600 centigrades. So that's the maximum temperature that you can use. This is the sensor example, so those small cylinders are the PT100s. If you want to go for larger temperatures, you need a different material than glass, so then ceramics is typically used. The sensor size can be small, can be large, so the ones that you have here are like 4 or 5 centimeters long, but it can be like this small, like maybe 2 centimeters or maybe 1 centimeter. But it's not a good sensor if you want to measure really small, something with some really small objects. Then you need a different type of sensor. If you want to go for higher temperatures, then the glass is not a good material, and you should use ceramic platinum sensors. They work for temperatures up to, let's say, 800 centigrades, so a little bit larger than the glass ones. The construction is a little bit different. The casing is from ceramics, and the wire is not embedded into the ceramics, but there are 2 small holes. It's like a tube with 2 holes, and the wire is freely moving in this hole. The advantage of this construction is that you do not add additional strain caused by different thermal expansion from glass and from platinum. So the wire is freely moving. If this ceramic casing is expanding, it will not have an effect on the sensor itself. So those are some examples of ceramic PT100s, or it can be PT1000, for example. So here you see all our PT100s, small cylinders, and they have either 2 terminals or they have 4 terminals. Sometimes you have 2 sensors in one package, so that you can measure from 2 sensors at the same time, and you are sure that the reading is correct. Or you have one sensor and then you have 4 terminals. This allows you to limit the effect of connecting wires between the sensor and between your instrumentation. We'll be talking about it also today. What you see here are the same sensors, PT100s, but in a surface version where they are much smaller. They are produced with a little bit different technology, and they allow you to measure temperatures on small objects or temperature fields. The third technology for RTDs is thin film. It's completely different. It's not based on wires, but it's based on thin films. And you have a ceramic substrate like this, and during the manufacturing process, a thin layer of platinum paste is deposited on top of it, and then the length and the cross-section will give you the resistance. The advantage of this thin film element is that it uses quite a small amount of platinum compared to the wire sensors, so it will be less expensive than the other sensors. I forgot to mention it here, but it was written, or it was not written here. Yeah, a glass PT100, just the sensor itself, is somewhere between 50 and 100 euros per piece. So the sensor like this can be, let's say, 3,000 Czech crowns, roughly. On the other hand, the thin film sensor will be like 100 Czech crowns. So it's about 10 times or maybe 30 times less expensive than the other sensors. But it's also less accurate. It's not as accurate as the industrial glass sensors, which are looking like this. And it can be definitely used for smaller temperatures than the ceramic sensors. Typically, you will find like 600 centigrades. Some manufacturers, they say 150 centigrades. So it depends on all the materials that are used for the construction. I have some examples of thin film sensors. They are here in this box like this. There are 2 of them. The size is roughly 1 by 3 millimeters. So it's very small. It has a small thermal inertia, and it will also have a small time constant. So a thin film sensor is good if you want to measure the temperature field on an object, and if you cannot influence that much the object itself. On the other hand, if you place that in some industrial application, you will definitely need to place it in a thermal well, which will increase the time constant. I have some more examples here. This is also a PT100. This time it's with a current output, and it includes a display. So this is just the thermal well itself, and it's mounted in the application, and it gives you current, and you can read the data directly locally on the display. So those are some examples of thin film RTDs. You see an example of price, $20 US, which is roughly 200 Czech crowns. So definitely less expensive than the glass or ceramic platinum sensors. Okay, platinum sensors are great, but they are really expensive. So it's not a good sensor for cost-sensitive applications. An example is if you want to measure temperature in a building, then you need a sensor in each room, and if the sensor itself would cost 3,000 Czech crowns, then no one would buy such a system. For those applications, you also need, you require or you want lower accuracy. So it's okay if the sensor for air temperature in a building gives you reading within plus minus 1 centigrades, for example. So you need a sensor that's less expensive and the cost will be lower accuracy. That's a good example where you can use nickel. Nickel is not as expensive as platinum, but nickel sensors will not be as accurate as platinum. It is good for applications with lower precisions, like household temperature controllers, where you want plus minus 1 centigrade, for example. Nickel has a higher temperature coefficient of resistance, so this means that the steady-state characteristic will have larger sensitivity. So in other words, the resistance for nickel sensor will change more than resistance for platinum sensors. On the other hand, nickel is really nonlinear in a larger temperature range. This is the equation for nickel sensor. And for this reason, we will be using nickel sensors in a small temperature range. So let's say 200 centigrades, maximum temperatures. If it's for something like a room temperature controller, it's not a problem. We operate that in, let's say, maximum plus 50 centigrades. So then it's non-linear, but it doesn't matter that much because we are operating in a small temperature range. There are also two accuracy classes, Class A and Class B. It's the same like for platinum. Again, Class A is more accurate and Class B is less accurate. If you compare the numbers in this table with the platinum table, you will see that this is definitely less accurate than the platinum sensor. The nickel sensor is typically called Ni 120. So 120 because it has 120 ohms for 0 centigrades. This allows you to distinguish directly if it's a nickel sensor or platinum sensor. You know roughly what's the ambient temperature, and around this ambient temperature you will see a difference. Here you see the steady state characteristic. The blue is the platinum 100, PT100. This orange is nickel. You see it's really nonlinear even in this small temperature range. And the black line is copper, which we will discuss in a few minutes. The nickel sensor typically is made as a thin film sensor. So it's looking like this. So it's a ceramic substrate and there is a thin layer of nickel on top of it, and it has this precise resistance. Nickel sensors are less expensive than platinum sensors, roughly 5 times. So this is an example of an Ni 120 sensor. You see 20 euros a piece. The sensor itself can look like this. So it's a thin film version, and the final product that you can find is looking, for example, like this, a temperature controller for controlling the air temperature in the room. In many cases, even this is too expensive. So in this case, you can use copper. Copper is really cheap compared to platinum and nickel. But on the other hand, it's really bad in terms of long-term stability. So if you take a copper wire or a copper statue or a copper roof, then it will oxidize very quickly, and this will change the properties of the sensor. On the other hand, there are applications where you don't care about this at all. An example is you want to read now what's the temperature somewhere in the application, and this measurement will take 1 hour or 2 hours, 10 hours. So it will not be a long time application. So for those applications, copper is quite good. And one example where copper sensors are used is, for example, to measure temperatures in electric machines. You want to measure the winding temperature of the electric motor, and you want to verify it, and you just measure the temperature, and it's done in 10 minutes or 30 minutes, and then you remove the sensor. So copper sensors, they typically look like this. See, they are very thin, and in an electric machine you have slots with windings, and you place the sensor in the slot, and it's thin, so it will fit in. Since copper, compared to platinum, has a quite small electrical resistance, it's a really good conductor, then the sensor, if I want to make the sensor with 100 ohms, would be really big. So for this reason, copper sensors, they typically have 10 ohms for 0 centigrades. So you will find names like CU10, for example. And the sensor itself looks like this. So it's a copper wire or copper layer deposited on some holder, and then you have some connecting terminals where you connect your instrumentation. One advantage of the copper sensor is that it's linear in a really large temperature range. So for electric machines, let's say we use up to 150 or 180 centigrade. So in this range, you see it has a really nice linearity compared to nickel, and even better than platinum. Any questions? Okay. The last sensors for temperature would be thermistors. The difference between RTDs and thermistors is in the material. RTDs are from metal. Thermistors are from semiconductors. Thermistors, they also change electric resistance as a function of temperature. But the material is different. And also the physical reasons for the resistance changes are different. There are two kinds of thermistors. One is called NTC and one is called PTC. NTC stands for negative temperature coefficient. This means that the electrical resistance is changing with temperature. With increasing temperature, is decreasing. And PTC is positive temperature coefficient. It means that electrical resistance is increasing with increasing temperature. It's not as easy. If you look on a typical chart for a PTC, you see that first electrical resistance is decreasing. So here I have a negative slope. This means I have a negative temperature coefficient. And then from a certain temperature, the resistance is increasing. So in this area, you have a positive temperature coefficient, and in this area, you have a negative temperature coefficient. Typically, PTCs are not used as temperature sensors, although you may find some of them, but they are used as temperature fuses. So this is a temperature, and when the temperature is larger, then the electrical resistance is increasing. It's also called sometimes resettable fuses. So you are normally operating around here. The electrical resistance is small. If there is a fault in your electrical connection, the current will be larger, and it will heat up the thermistor, and it will disconnect the circuit. When it cools down, it will connect itself again. We will be talking only about NTCs as temperature sensors. From the chart, you see that here we have not a linear dependence between temperature and electrical resistance. This will be one of the disadvantages of the thermistor. The dependence between electrical resistance and temperature is approximated with an equation that is called Steinhardt Hart equation. And it's only an approximation. So it's an approximate description of the reality. It typically looks like this. You see, it's an exponential equation. And if we want to express the electrical resistance from this, we can remove the logarithms and we'll have an exponential response. The exponential response typically looks like this. So you have some coefficients that are given by the material constants. You don't need to remember this at all. I just want to show you that it's an exponential dependence. And those coefficients, B, C, X, and so forth, they depend on the material. So a typical thermistor looks like this. Typically, the electrical resistance is given for 25 centigrades. So if you look into a data sheet, you will find that 20 kilo ohms for 25 centigrades, for example. That's roughly here at 0. 25 is here. And you see that the electrical resistance is really changing with temperature. So here, if I would use this same thermistor for minus 40, I would have about 800 kilo ohms. So there is a really large change of electrical resistance as a function of temperature. This is quite different if you compare that with PT100, for example. So a thermistor will have much larger sensitivity than the other metallic RTDs. That's one advantage. But the disadvantage is that you have a nonlinear dependence, and we will have to handle it somehow. So, if you want to use a thermistor in your application, the dependence is exponential. You typically find the coefficient in the data sheet from the manufacturer. And in practical applications, this always leads to a table that you have stored in the microcontroller. So you have a cheap sensor. You have a sensor that has quite good sensitivity, but compared to a PT100, for example, you will need a much more complicated electronic circuit. So then that's a trade-off. Do I want a sensor that will be reliable, that will be accurate, but very expensive? Or can I use this sensor that will be really cheap, but then I need a more expensive electronic circuit? Thermistors are also quite sensitive with regards to mechanical and chemical damage. So if you have a thermistor like this, you also need to protect it in a thermal well. So there are thermal wells for thermistors. They look like this. It's again a small tube where you can find where you can place the sensor itself. Here are some thermistors as well. So that's just that element itself. It looks like this. It's typically a very small ball from a semiconductor material. The diameter is a few millimeters. So it can be very small, like 0.2 millimeters, or it can be a little bit larger, like 3 millimeters, for example. If you compare the sensitivity of a thermistor to a PT100, this is much better. It has much larger sensitivity. On the other hand, you cannot interchange thermistors in the application. It's not as accurate as PT100s, and every time you exchange a sensor, you need to recalibrate it. That's a very large disadvantage in industrial systems. So thermistors cannot be used without recalibration. Here is an example of a thermistor in an industrial application. So usually thermistors are used in a problem is in positive temperatures, because for larger temperatures than roughly 150 centigrades, the semiconductor material gets damaged. So semiconductor sensors are used up to 120, 150 centigrades, and not for larger temperatures. If you want larger temperature, you should use a PT100 or a thermocouple. In negative temperatures, it's not as bad, so typically, let's say, minus 80 centigrades is fine. The accuracy is not that bad, but if you compare it with a PT100, it's not as good as a PT100. If you look on the price, this is the price, the sensor plus the circuit itself. So it's roughly 5 times less expensive than a PT100. But this includes the electronic circuit as well. If you want to use thermistors yourself, this is an example of a normal thermistor that you may buy in any electronic store. See 8 Czech crowns, sensor itself, so it's really cheap. On the other hand, it's a nonlinear. It's not as accurate. You see like 10%, it's typical accuracy, or 5%. But it's quite fast. Here, this sensor has a time constant of roughly 1 second. So if you want to measure really fast changes of temperature, then thermistor is a very good sensor. For example, if I would take this PT100, it would have a time constant of, let's say, 1 minute. So it's really accurate, really expensive, and really slow. This is fast, cheap, and has a back accuracy. Okay, how to handle the problem of nonlinearity? We know that the steady state characteristic looks like this. So we have a nonlinear dependence between temperature and electrical resistance. There are 2 ways how to handle it. One is to do it in the, let's say, electrical way. You take the thermistor, you connect a serial resistor and a parallel resistor to it, and in a very small temperature range, this will give you a linear dependence between resistance and temperature. I say a very small temperature range, so if you want to linearize it, let's say around 25 centigrades, this would probably work in the range of plus minus 5 centigrades. So it's a good way if you want to build a temperature control for a pool where you want water temperature between 20 and 30 centigrades. But if you want to use it in a larger temperature range, it will not work at all. You can test it yourself. I have made an online simulation that you can open, and you will see what will happen if you are changing the temperature. Basically, you will see that it's accurate for the temperature where you linearize that. For any other temperature, it's very bad. The second possibility is that you have a microcontroller, and this microcontroller has a stored table with data from the manufacturer. So it means that you basically have a dependence between resistance and temperature stored in the memory at some points. So, for example, here, 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 and here. And you interpolate the actual measured data in real time. So then you have a cheap sensor, but you need a more expensive microcontroller with a memory. It will calculate something, and then the output will be some standard signal like a voltage, current, or some digital bus. So this is actually the preferred way today. Microcontrollers are really cheap, so even the sensor is not as good as it could be. You improve the properties with additional electronic circuits. Okay, and last part for today is circuits. How do we connect the sensors to a computer or to some voltmeter that will read the temperature? We will discuss only circuits for RTDs, so PT100 especially, and thermistors as well. We will not discuss any circuits for thermocouples. So the basic circuit that we use for RTDs is a bridge. And we will discuss only a Wheatstone bridge here. For a PT100 that I will use as a typical sensor, you see the sensitivity is quite small. The electric resistance is changing very little with temperature. So we need a circuit that will work as an amplifier and will amplify this small change of electrical resistance. And we are changing electrical resistance, so we will use a DC bridge. And we will not use any AC bridges. Now the worst thing that you can do in the circuit is that you take the sensor and connect it with two wires to your electronics. So this is an example of how you should not do it. The bridge has 4 resistors, R1, R2, R3, R4. This is the sensor. This is placed somewhere. This is placed in a thermowell. And there are long connections between the sensor and between the bridge itself. This can be 1 meter or it can be maybe 100 meters. Depends on your application. And if you connect it with a 2-wire connection, you have a problem with those connecting wires. Not with their resistance, but you have a problem with changes of this resistance with temperature, which will definitely happen if the sun starts shining, if someone opens the window, then the resistance of those wires will change. And even if it's a very small change, it will have an effect on the output signal. The output signal is here on those 2 terminals on the bridge. It's a voltage signal. And we will learn, I think in 2 weeks, that you can write this equation. R1 times R4 equals R3 times R2. This is called the equation of balance for a bridge. And it's basically saying you that the output voltage will be 0 if you have the bridge in balance. So it means that if you have R1 times R4 equal to R2 and R3. So you can either have an unbalanced bridge where you directly read the output voltage, or you can have a balanced bridge where you are changing the elements in a bridge in order to achieve 0 here. And if you look on this equation, it's not just the resistors R1, R3, R4, but it includes also all those resistors that are in this position, So if there will be some changes in the resistance of the connecting wires, I will unbalance the bridge and I will not be able to distinguish if this change was caused by the change of temperature, which I want, or if it was caused by the change of the temperature of the connecting wires, which I don't want. This is an example showing how important that is. This is an example of a cable that is used for Ethernet. I'm not saying that this wire is used for connecting sensors. I've just selected this cable because you know how it looks like. So this wire has roughly 0.19 ohms per meter. If your connection is 10 meters to the sensors and 10 meters back, then you have 20 meters of wire. Let's say there will be a temperature change of 10 centigrades, and this will cause you around 76 milliohms in resistance. Now, if you compare that to a PT100, then we know that PT100 has 0.39 ohms per centigrades. So it's smaller but it's definitely significant because you have something like this, 0.076 ohms. So the change of wire temperature has caused a relatively large change in the electrical resistance that we have connected into the bridge. So this kind of connection can be used in applications where you don't care that much about accuracy, and in applications where this distance is small, and in applications where the temperature is not changing that much. So you may find it in a lab, for example, where this distance will be 2 meters, where we know that temperature is changing between 20 and 25, and that's it. And this will not be that significant. In industrial applications, you need to use a different kind of connection that will handle this problem with temperature changes. And this is the 3-wire connection or the other connections that will follow. How does it work? Here we have a bridge as well, so we have 4 resistors. But now our temperature sensor is connected with 3 wires. So if I look in my equation of balance, then this R4 includes this wire resistance and this wire resistance. And R3 includes this wire resistance and this wire resistance. So if the wire temperature is changing, let's say if it's increasing, then electrical resistance will increase. So R4 will increase, but R3 will increase as well. And those variables are on the opposite side of the equation, so it will cancel. So this 3-wire connection eliminates the problem of changing wire resistance with temperature. You can try again the online simulation. You will see that changing the temperature will not have an effect on the voltage that you have on the bridge output. So this voltage will be virtually independent on the resistance of the wire that you have in the circuit. The second option is that you use 4 wires. And 4 wires means that you have 2 wires connecting the temperature sensors, and you have 2 additional wires from the bridge just going to the same terminal box and back. And we are assuming that those wires will change temperature in the same way. So if this is changing resistance, this will change resistance in exactly the same way. So this also compensates the effect of temperature changes. The last connection is called a 4-wire connection, and it can be used for RTDs, but it can be used also for thermistors. The bridge is mostly for RTDs. This is for both. Now the goal is that I want to read the resistance as a function of sensor temperature. So we are providing a constant current through the circuit. This is a, let's say, electronic circuit with transistors typically, or operation amplifiers that provide constant current regardless of the wire resistance and sensor resistance. And here we have some current. And here we have a voltmeter with a very high input resistance. And very high input resistance means that the current flowing through this connecting wires will be almost 0. And if it's almost 0, it means that there will be no voltage drops, and I'm reading directly the voltage that I have on the sensor. So this connection is used typically for thermistors, because thermistors, they have high sensitivity. It means that this is changing a lot with temperature. It can be used also with PT100s, but here you would have a small voltage that you need to read. So this is a better connection for thermistors. Now note that here there is some current that is flowing through the sensor. The same is happening also for the bridge connection. There is always some current that is flowing through the sensor. And from physics, we know that joule losses are dependent on resistance and on the square of current. So if you increase the current that is flowing through the sensor, you are increasing joule losses. And joule losses mean self-heating. So the sensor will self-heat and will be used as a heater, and you will not be able to read the accurate temperature. So for this reason, you need to limit the sensor current to a certain limit, and the recommended current for a PT100 is 1 milliampere, and for a thermistor it's 50 microamperes. For thermistor it's much smaller because thermistors, they have a much larger electrical resistance. So we have a small number here, but here you have definitely larger number. So for PT100 we had 100 ohms. For thermistor you typically have something like 20 kilo ohms. So to finalize this, let's compare the three sensors. So thermocouple gives you voltage. The voltage is a function of temperature difference. It works in a large temperature range, the largest out of those three. So a thermocouple can easily work up to 1500 centigrades. RTDs can work, well, this is in Fahrenheit, but RTDs, they typically work to 600 or 800 centigrades if we are talking about platinum sensors. And thermistors, they work up to 100, 150 centigrades, roughly. Interchangeability, the best is RTD. This is not bad, but this is the worst. So if you want a cheap application, low accuracy, then go for a thermistor. If you want long-term reading, good reliability, interchangeability, you need to go for RTD. If you want large temperature range, you need to use a thermocouple. Also, for an important thing is the response time. They are roughly the same, but here it depends on the thermal well where you install it. But if you compare RTD and thermistor and thermocouple, let's say bare elements, then typically thermocouple is the fastest, then you have a thermistor, and then the slowest one is the platinum sensor. Here are some industrial examples of contact temperature sensors. So this is a sensor in a tank, in a thermal well, looks like this. Thermal well is from the outside, so then the thermal well is placed in the tank. If you need to remove the sensor, you just remove it from the thermal well. Those are heat exchangers, and here it's a glass thermometer, and here there is a platinum sensor. There is a little bit better picture here. So this is a platinum sensor here installed at the heat exchanger. The same here, so platinum sensor installed in the elbow. The same picture, well, again the same. This is a picture of a PT100. This was an application for measurement of exhaust gases from some burner. So a PT100 in a thermal well and current output. Those are thermocouples, so installed in the elbow, thermocouples in a thermal well. Again, this is a PT100, roughly to the middle, measuring exhaust gas temperatures. Those are thermistors. Since the thermistor is quite sensitive, this is installed on a copper tube from the outside, and it's measuring the temperature. This was some refrigeration application, and the copper tube has a quite good heat conductivity, so it can be installed from the outside. Water temperature measurement, so plastic tube, T-piece, and temperature sensor in this T-piece. Again, this thermistor. This is a PT100, I believe. You see it's inclined like this, so the flow direction is from bottom to up. And again, some other pictures of PT100s in several applications. So here you see this is the temperature sensor installed over here. Temperature sensors here installed. And I think this is the last picture. No, before last. This was some pharmaceutical application. Again, PT100 with the terminal here. Questions?